Hi, everyone. I'm Ihor again from Kry10, where we're developing a platform and operating system for resilient systems and reliability. So what's the most reliable thing you can do when your computer's not working to get it to work again?
Turn it off and on again.
Right. You turn it off and on again. Works 100% of the time. So this talk is going to be about that. So what I'm going to talk about is, I'm going to go into more detail about why that works, restarting your computer works, and then how we can use that to build more reliable systems. I'll talk about how this idea is used in Erlang, let it crash, and then how we can apply that to SEL4, how we apply that on the Kry10 OS, and then what some of the challenges are of doing this and how we get that, how we might deal with those challenges. So why does it work when your system's not working and you restart it and it works again? Well, typically your system stops working because of some kind of erroneous state. There's some state in your system that's causing it to behave incorrectly. And the reason why we restart is because we're not sure what that state is, right? If we knew what it was, we could fix it, but typically we don't know what it is or we don't want to bother finding out what it is. So we start it again and the state gets cleared, it gets reset to a known state, it's a clean slate, and ta-da, it works again, right? So we reset it to some known state, and everything works again until it encounters the erroneous state again or a different erroneous state, and we do it over again. Some systems require more restarts, some systems require less restarts. But it works. Now, the problem with restarting your whole system is that it's a pretty drastic approach, right? Restarting everything. It gives you a large downtime, right? Rebooting your system is expensive, takes a long time. You have to wait for it to start up. But you also lose good working state. If you're working on your system, you've got stuff in memory, you've got state that you've worked on, and you restart, then everything goes away and you lose that good state. You have to rebuild it all again, or maybe you've lost it forever and you have to try to remember what it is. And of course, it might not actually fix the problem. That erroneous state might still be there when you start up, and it'll stop working again or crash again, and restarting it won't fix it. So it doesn't always work. It works a lot, but it's pretty drastic. So at Kry10, we're building systems that have protection, resilience, and lifecycle management. So in this talk, I'm going to focus on the resilience part of it. And so a big part of resilience is reliability. We want systems to be reliable, to keep running, not to have to restart them all the time. We don't want them to crash and so on. And restart is good. We want this clean slate. If something goes wrong, we want to be able to get a clean slate, but we don't want this large downtime, so we want to reduce the downtime. We want to reduce the loss of the non-erroneous state. So all the good state we have, we don't want to throw that away. It's like throwing the baby out with the bathwater. And we want to deal with these persistent failures as well. Somehow we need to deal with those, right? So when restarting it doesn't actually fix the problem, how do we deal with that? So Erlang OTP introduces this let it crash approach. Now, last year I talked about Erlang and I had a somewhat in-depth introduction to Erlang. I'm going to do a much shorter introduction because this is a shorter talk. Basically, Erlang is a programming language and a platform that was developed at Ericsson, and they used it for developing highly reliable systems, network switches, phone switches, and so on. It consists of Erlang, which is a functional programming language that has actor-based concurrency. The idea is you build systems out of a lot of processes and they communicate with each other asynchronously. And OTP is a platform for Erlang, which consists of a bunch of things. Some of them are design principles. So how should you build your systems? How should you build your applications? As well as libraries that help you build according to these design principles, and tools. So it's really everything in one. And Erlang introduces this idea of let it crash. So if you're running code and you encounter an error and you don't really know how to deal with it, don't try to figure out how to deal with it, just crash. And the reason why it works is because OTP has this concept of supervision trees. So you build your system up according to these supervision trees, and you have worker processes, but then you also have supervisor processes. And your system runs, and then if one of the processes crashes, so let's say worker 1 encounters an error that it doesn't know how to deal with, it crashes, the supervisor gets notified of the fact that this worker has crashed, and the supervisor can then decide what to do. And the supervisors typically have a handful of strategies that they do, but typically what they do is they restart it with a new state. And the connections are all the same, and it basically takes place of the original process. What else? So supervisors have different strategies. So if another worker crashes, it could restart that worker. It could also decide to just restart all the workers. In this example, it doesn't. But supervisors themselves are also supervised. And so if a supervisor crashes, then it'll kill its workers and then get restarted and then restart its workers as well. So this is the idea of let it crash in Erlang. If you run into a problem, don't bother having really complicated error handling code. Crash, restart, and the supervisor will take care of it. So why does let it crash work in Erlang? There's a bunch of kind of prerequisites and requirements for it to work. First of all, Erlang encourages and OTP encourages a distributed architecture, so there are a lot of communicating processes. So the processes are smaller, they communicate with each other, they're isolated from each other, so you can restart them. So process isolation is the other one. The processes don't share resources. So if you restart a single process, it doesn't affect any of the other processes. There's explicit communication, so you can transparently recreate and reuse new connections. So if you start a process, you can transparently now talk to that other process rather than the old process. And a lot of the processes are stateless in Erlang. So Erlang's a functional programming language. It encourages having immutable data structures and so on, which makes it a lot easier to build stateless processes. But OTP also provides design patterns that encourage splitting applications into stateful parts and non-stateful parts. So the non-stateful parts just process things, but they don't actually keep state. So you can really easily restart those. And then you have the stateful parts that you have to be a little bit more careful about. So let it crash is a really good approach in Erlang. It works well. It's been used a lot to build really highly reliable systems. So that sounds like a good thing to do if we want to build reliable systems. Can we do that for SEL4 as well? Well, is it a good match? Do we have a distributed architecture? Yeah, mostly. We've heard that it's a good idea to build SEL4 systems as a bunch of components that communicate. So that's similar to Erlang. Does it have process isolation? Yes, that's kind of what SEL4 is known for. And does it have explicit communication? Yes, we set up endpoints and notifications and shared memory channels between processes. So it is a pretty good match. It has a lot of the requirements there. In terms of mechanisms that we need, the things that we need to do for a let it crash type approach, we need to be able to detect faults. So SEL4 has fault endpoints, so we can detect when things go wrong with processes. We need to be able to tear down processes. So the capability model that SEL4 provides is really good for that. If you set up a process with, allocating all the resources from a single untype, then you can easily revoke that untype, for example. So it can be pretty easy to tear down processes. And starting new processes, again, you can allocate everything you need from a pool of untypes or an untyped you have. So yeah, we can start new processes as well. Not in all kind of platforms. We have some static platforms where that's not things we do, but in general, SEL4 allows you to do that. Some of the challenges for doing this in SEL4, well, a lot of SEL4 systems are static, so we don't have easy mechanisms for actually restarting processes, restarting communication channels, and so on. So that's a challenge. And then not all of the state that you have to reset when you restart a component is software state. So especially for drivers, you might need to reset drivers or hardware state. So if you're resetting a driver, you need to reset the hardware to a known state as well. SEL4 doesn't really provide anything for that. And then it doesn't really provide any answers for how to do stateless processes, how to deal with processes that have state that you can't lose, that you don't want to lose when you restart. So there's still some challenges. This is where Kry10 and Kry10 OS come in. So we've implemented this kind of let it crash approach in Kry10 OS, inspired by the Erlang OTP approach, but different. So we don't do supervision trees, but we do a dependency graph. So this is an example of a simple system with dependencies. So the arrows kind of say what components are dependent on which other components. And this is our root task, which acts as the fault handler and as well as this process restart manager. So we run this system, And let's say there's a problem in the tunnel component and decides to crash. It notifies this root fault handler, and it starts the recovery process. So it looks at the tunnel, and it looks at the dependency graph, and looks at what depends on that tunnel. So we see the admin and the weather station are dependent on it. So it kills those, then it cleans up after the tunnel, and then it starts and restarts all the things that depend on it. And then it's done. And then we've got the system that's recovered and restarted and running. So it's pretty straightforward. And it relies on a lot of the functionality that we also use in the Kry10 OS to deal with updates. So kind of updating components and restarting it. It uses the same code for that. So there are a couple of challenges that we still have to deal with. The first one is how to decide whether you should crash or not. Right? Which components, so when is it not useful to crash a component? You don't want to crash a component if you can recover from the error. There's no point. If you know what the error is, if the error is something you expect, something that you can reasonably recover from, then there's no point in crashing. You can just recover from it. It's not useful to crash a component if the failure is not caused by the component state. So for example, if there's some hardware problem that's causing your errors, then restarting it won't necessarily solve anything. If the failure is not caused by erroneous state, so if it's correct state, but you've got an implementation problem in your component that can't deal with some correct state and is causing a problem, restarting probably won't fix it because you'll get that good state again and cause a problem again. If the component contains critical state, so you can't afford to lose, then you don't want to just restart it without saving that state somehow, because then you'll be in trouble. And then if the erroneous state is persistent, if it's still there after a restart, then it doesn't necessarily help to crash it. So in particular, talking about this critical state leads to this idea of the error kernel in a system, and which is the set of the components that contain critical state in a system. These are the components that you can't just crash for reliability. As with kind of microkernels and so on, the goal is, or secure systems and their TCB, the goal is to reduce the size of that error kernel as much as possible. So reduce the number of components that have this critical state that isn't saved, that they can't afford to lose. And so you really need to kind of focus on designing your system and splitting it into components that store state versus computational components. And this is one of the things where OTP design principles and patterns really encourage this. And we need to look at how to encourage that in building these kind of reliable systems. And then the other challenge is how to deal with persistent failure. So what do you do if your component keeps failing? So your component runs, encounters an error, restarts, runs again, and re-encounters that error and keeps restarting. This could be a pretty bad situation. Basically, you use heuristics for this. So you can have a restart count. So restart the component. If it fails, restart it again. Do it 5 or 6 times. And if it keeps failing, move on to the next thing. The next thing could be to increase the restart domain. Maybe the component is getting some state, some input from another component that's providing it bad input that's causing it to crash. And if you don't restart the other component, you keep getting that bad input. So increase the restart domain and restart some more components, and maybe that's going to fix your problem. So try that. If that doesn't work, maybe the problem is some persistent state that keeps causing problems. So maybe you need to look at your persistent state and sanitize that, check that state, and see if you can clean that up in some way to stop the problems. Ultimately, if that doesn't work, maybe the problem is in your code. You want to either reinstall the component code, maybe something happened to corrupt it, or revert to a previous version that works, or update the component code in some way. So try to fix the code problem. And then eventually, if nothing works, you give up. Right? You just tell them, we can't go any further. This is the best we can do. And that's sometimes a lot better than just trying to continue running with bad code or bad input. All right, so that was kind of a very quick introduction to let it crash and how we can use that for reliability. Basically, when we restart, we have a clean state, and that gives us a much better chance of successfully executing. This is inspired by Erlang OTP and let it crash. We can apply it to SEL4 and Kry10 OS because we have the right mechanisms underlying to do that, and we've done that on Kry10 OS, but there still are some challenges. crashing isn't always possible, so we need to design our systems to reduce the error kernel. And then if we have to deal with persistent failures, then we need to use heuristics and eventually give up. Thank you.
Okay, thanks very much.